Subhuto, I have been able to join.
So, are we live now?
Yes.
Can we start the session?
Yeah.
Can we start the webinar?
Yeah. Just hello.
We are live.
Okay, I think we are now live. So we are starting our webinar. Here, thank you all.
Actually, it's raining very heavily over here. That's why some problem from my end is going on. Hello. 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 Oh, Subhuto is out. Gautam, can you listen?
Yes, sir. Yes.
Gautam Burman.
Yes, sir. Yes.
Subhuto is out, perhaps.
He is
Subhuto
joined now.
will rejoin, of course.
Hello.
Yes.
So
Yes, yes.
there was a will enlighten us on application of statistics and data analysis in banking sector. Our second speaker will speak about a very interesting topic from confusion to conclusion, a tale of p-value. I thank both the lecture for us. I also thank officer in charge of Government College, our Teachers Council Secretary, Dr. Amar Mondal, my fellow colleagues, and Indrita Saha for technical assistance.
My completion of my postgraduate studies. And there I worked on credit risk model development and validation. And what I would like to talk about today is mostly leverages on my experience at that time. So I have a presentation I'd like to share with you now. Let me try that. Okay. Are you able to see my screen?
No,
No. Okay, so let me try again then. Okay. Right now?
yes, yes.
Yes, we can see.
Okay, great. So my statistics and data analysis in the banking sector. So this is a very broad topic, and I'll just touch upon a couple of points here. So as I mentioned that I have some experience in credit risk modeling and validation, so that's something that we are going to talk about mostly. But apart from that, in the course of my career, I've also looked at and about other applications, so I'll talk about that. But obviously, banking sector is huge, and there are so many different applications. These are only a couple of them, not like a list. So first, so let's talk about, before we jump in, let's talk about what kind of banks are there. So there are two deposits, and you have subcategories in commercial banks depending on the kind of customers they have. So you have retail banking, which deals with individuals and very small businesses. Then for banking, which deals with large businesses. And we also have private banking, which gives wealth management services and such. So into one commercial bank. On the other side is investment banks, which deals with all activities in the financial markets and perform in a stress scenario. For example, like right now, we saw that the COVID-19 crisis was quite a stress scenario. It's had a very strong impact on the markets. So that's something that you would like to see, be prepared for so that you are have enough capital if you need, enough liquidity to kind of to survive during the stressed scenario. So that is stress testing. Then there is a business intelligence, where you use statistics and data analytics to kind of improve your business performance or card or a loan or anything like that. Then there is an use of early alert system. What that is so if you, for example, if you have extended a loan to a customer and they are going to pay off maybe over 10 years. So every year you want to check their credit score. You want to see if they're paying, regularly, if they have defaulted, if they have been delinquent, which means that they have paid later than when they were supposed to pay, but they have paid. So that's kind of between like paying on time and defaulting. There's a phase called delinquent. So you want to see those kind of behaviors to see if there is a chance or an inclination of the customer kind of closer to default. So when you have this kind of behavioral, you have this behavioral information and you can use that in a model, then you can see if they're kind of getting riskier over time or not. So that can help with the, so that can, you can alert, create an alert based on that. So you can be more observant towards that individual. You might want to, talk to them about, changing the, the loan, the payment arrangement, or if there's a credit card, you might want to see if there is ways to give them an offer, an option of kind of spreading the balance over a period of time or things like that. So you can see if there needs to be any kind of special arrangement for the customer. So that's an early alert system. Then crossing on products or credit limit management, that's very important as well. So if you see that a customer is paying everything, like they have a credit example, and then they are paying on time and they're spending a lot, then you might want to increase the credit limit so that they spend even more, and then you get more money from that customer. So again, the credit score will help you to assess if they are, they're likely to, if they're more likely to pay off, then you can give them a higher credit limit and be more confident that they're going to be able to manage. And cross-selling of additional products as well is kind of, it's more of a, so we'll talk about the kind of business intelligence part a little bit more, and it kind of fits into that more, that you can use this information to see if there are any additional products that you can offer the clients. So these are the couple of reasons why. And another reason actually to use to score a customer is you want to know what kind of portfolio you're working with, and what kind of overall you have on books. You want to know what kind of likelihood they have at an overall basis to pay you back. That's what kind of helps you to calculate what lead to how much capital you need to hold. So the capital, so the need to hold capital is something that's to make banks more stable. So it's a regulatory requirement. The central banks like RBI would want you to hold a certain amount of capital if you're doing a certain amount of business. It's because if you're using all your money to, give out as loans and credit cards, if there is a scenario where people are coming to you to take their deposits back, running into, or they're not paying you back, then just money as a bank, and that is not ideal, obviously. So that's why you need to keep enough capital. That's why it's very important to understand what risk levels you're dealing with. So that's another reason why it's useful to do like regular credit scoring of customers, so that you know how a recent how the risk levels look like at a recent point of time. So the next one is like, how do banks score customers? So most of the times it's logistic regression is very is what I have worked with when I was in the bank, and I've spoken to friends who are still working in these sectors, and it's most popular because so what essentially you're trying to estimate is the probability of default, which is from 0 to 1, and what you do is you try and you identify key variables that sort of tell you about the customer's behaviors, and then you can use logistic regression when you find the variables that are most material of the whole portfolio, and then, as I mentioned earlier, we have probability you score. So let's say that there's a probability of 0 to 1% probability of default, that they have credit score of, let's say, 0 or 1 plus. Then if it's 2 to 1%, then it's like 1 and then 2. So something like that. So the higher the probability, the lower in the scale you go. So a couple of like variables that, so one interesting thing is that when you're actually applying for a new credit card or a new loan, the banks don't have any information about you. So they can't see your past transactions because you're a new customer. So what they rely on is like something. So they look at your, for example, if you're working or if you're a student, if you are, what's your salary, what's your age. Interestingly enough, sometimes if you're married or not. Apparently, if you're married, you're more stable, and things like that. So it's kind of, and so it's kind of a, in the, when it's a new application, it's kind of hard to assess the person very well. So I think the credit scores also help when it's you get credit score from the credit agencies. Another important thing with models is to cross-validate models. So we have to, so you can do, so when you have a sample, like you have like 100 data points, you use 70 data points to build the model, and then the remaining 30 or 60-40 split of in sample out sample, you need to be able to cross-validate your model so that you're not overfitting a model. So this kind of stuff, that it's actually, when you're building a model, it's kind of a lot of iterations that happen. So because you want to find, so the model that works quite well when you cross-validate as well. So that's kind of a very like basic description of how the modeling happens. So a couple of key challenges when you're developing a model. So one is, sometimes like the data quality is always a challenge, and you see no matter where you work, if you're working with data, it's always going to be a struggle. And it's, at least to me, it was like the most like not rewarding as well, kind of a bit boring work to do. As the data cleaning is very important. So you need to check for, and because sometimes in the banks, the people who enter the information for clients is quite like free flowing text sometimes. So it would be ideal if you have like drop downs when you're feeding the information to the system. If you have drop downs, or if you have like very specific constraints of what kind of formatting can be entered for each field. But often that is not the case. And you'll end up getting like all sorts of information in the data set. So you need to check for missing data, obviously. There are a couple of fields, I mean, most fields, and if you have like 50% missing data, you can't use that field. So sometimes you might want to think about what that might mean. So for example, if there is a yes or no question, maybe if it's missing data, it is by default no, but it's really hard kind of what it means. So often you'd have like, if there's like X amount of missing data, you don't use such data. And then you have you can have historical defaults, but that is something that I personally dealt with as well, because I was working in wholesale modeling, and that that entails like middle market, like quite big corporations. And some of them, there was one portfolio that was really large corporations. And to start with, the portfolio was like quite small. And it was Australian New Zealand Bank, so their portfolios are usually not as large as quite a lot of like the US banks, for example. And these corporations that I was working on, it was like quite small. I think it was about 100 corporations, and they're like really large, so they don't really default. It's not like, you know, having a 30,000 sort of credit card portfolio or something. So it's really hard to find how to kind of assess if they're going to default or not, if they've never historically, you know, defaulted. So that was quite a struggle because then the statistical modeling, it just doesn't work for if you have a really small portfolio, and on top of that, if it's really, you know, good clients, they don't default. So at that time, so what we did was we first, there were corporates. So one good thing about that is that you have these rating agencies. Like you'll have the credit ratings for most of them from like Moody's or S&P and Fitch, and you can leverage that, use that as a sort of proxy, or use that as a key component to your model. And apart from that, what is useful is expert models. So that's not really statistical. It's kind of it's to some extent logical, and it also involves expert opinions. So we'd go to you know, different businesses and like the front office guys, the managers who deal with these customers, and we'll ask them about what kind of. So we'll go to them with a list of questions for that, you know, and for each of these. And we'll ask them that, okay, so if for this big corporates, you also look at their, you know, boards of directors or their reputation in the market and things like that. So we'd ask them that, what do you think is the most important? And that's how we'll give them some weight to these questions and to the answers. And that's how kind of we worked around this problem of not having enough defaults. It works to some extent, but there are challenges even there. But let's not go into that. It's going to take a while then. So these are a couple of elements. So again, I'm not going into much technical details here. As you see, there's like in my presentation, there is like no formula, nothing very statistical. I'm just talking more about the applications and kind of a broader sense of where it can be, you know, useful. And you know, these days you find like all sorts of information online anyway. So if you find something interesting here, you should, you know, you may want to just look it up online, and you'll find a lot of details. So that was credit scoring. So I think I've covered most that I can remember. But yeah, I might have missed a lot, some use cases or some details, but again, you can find more details online and from credible sources. So if you find it interesting, I'd suggest look it up. So the next point I'd like to talk about is model performance analysis. So once you have a model, so you've developed a model to credit score customers, for example, how do you assess if it's performing well, and if it's, you know, like if it's doing what it's meant to do? So one way to look at it is like you. So you don't, as I said, like it's an iterative process to develop a model. You don't just develop one model and be happy with it. It's usually you try several different ones. And benchmarking is really looking at one model, comparing it with another, and see if you've done a, if you're satisfied with the kind of model you have. And then backtesting is trying to see how your model. So, for example, if you have so it's kind of there's an analysis called realized versus predicted, which is basically so let's say you have a portfolio of 100 people, okay, and you know that you have certain of the probability of defaulting, right? And what you can do is you can see if it's actually defaulting or not. So you can see that your estimation from the model and actual occurrence, how they align. So that's how you can assess if model performance is fine or not. And that's something that it's usually you have to do it quite on a regular basis. It varies from portfolio to portfolio and model to model, but something that's very important. It's also like backtesting is pretty much like you see it not just for these models. You see it's one of the very important for all sorts of models, to see if it's performing over a period of time. So this thing that validator of the model, the validate model on a periodic basis. It could be again on an annual basis or years, depending on how important the models are, how the models are developed. So that's something that while the model developers do, but model validators on how the you have some sort of 50% from the US model kind of has a sort of like it captures more of that characteristic of from the region. If you have different behaviors in different regions, as well. So there are a lot of testing that goes on. It's during the development phase, but also at an ongoing phase, and as long as the model exists. So that's another. So that model performance needs a lot of statistics as well. then comes stress testing. So kind of macroeconomic as well, because the variables by this much. How is that impacting your the losses or your profits? And so that's something and so that's how much you can. So you can say that, okay, so under stress scenario, so I expect that if we would we might lose up to 100, say like $100 million or something. So and then that would be something that you need to use it in your capital calculation. So that's something that that is statistics is used in. Okay, so the next one is business intelligence. We talked about it a little bit. And so this is basically using the customer data to kind of solve business problems. So for example, if you have you're not launching a new product, let's say, if you have your existing credit card customers, you can offer them, like, let's say, a personal loan. And how would you use statistics for that? You can use the transactional data that they have. You can see the customers that have been paying on time, that have got a good sort of good salary, but haven't taken a lot of credit already. And it's hard to tell like what the variables would be. That is part of the whole exercise. But so you can use your existing customer base to kind of try and get offer them additional products and things like that. Or even if not additional products, you can offer them like credit limit increase. You can offer them like discounts and things like that. And then fraud detection is, again, something that is quite interesting. And how that works is if you have like historically fraudulent data, and if you can see like patterns, for example, a lot of fraudulent activities you see in like shops where there's a huge, it's a large transaction. That can mean that's a potentially fraudulent trigger. And that's because that it's easy to kind of, you can buy the goods and then sell it off in a, black market or whatever. So that's something. Then if you're traveling and if you haven't let your bank know if there is a transaction in a foreign country, then that's a trigger for fraudulent activities. But these are like very basic ones, but it can be really sophisticated, the modeling for fraud detection. And apart from like, there is a lot of use of data mining in fraud detection as well. So yeah, so that's, and then I think I'm nearing the end of my time and also the presentation. That's good. But I just briefly touch upon the market risk analytics. This is something that's
sort of introspection, and for those who are using it and day out, day in, day out, some warning that you shouldn't use p-value without much protection. So that is from where I will start my talk.
Hello,
Yeah.
sir. Your presentation not visible.
Okay, hold for a second. Why it's not. Okay, just a minute. What happened to this? Now can you?
No.
Okay, okay. So why this lecture? Actually, a few years ago, there was a psychological journal called Basic and Applied Social Psychology. They, in editorial, they wrote that any paper which is the inference based on solely p-value will be banned from publication. So this is some sort of attack on the p-value culture or p-value world, because we always believe that p-value is the value that we want the value to be less than 0.05, and what we get what we call moksha. But this is something very interesting that had happened, that a psychology journal, they just ban any paper. So it was followed by another journal, the Good Journal Political Analysis, in 2018. So in the meantime, after the banning of this p-value concept, you can, in 2015, they issue they want beta, that is probability of type 2 error, should be as small as possible, 2. Okay, and the power is 1 minus beta. Look at this picture. So I think the type 1 error, for the people who works in the biology area, they are quite familiar with false positive and false negative. I think this is the perfect example of false positive and false negative. And you can see the first one is the type 1 error and the second one is the type 2 error. Okay, so here now let's go back to Sherlock Holmes. Some crime has happened and the null hypothesis is that it's an accident. And against the alternative hypothesis, it's not an accident. Now what Sherlock is saying, unlucky chap Watson. So what we want, whenever we have something like this, so what we will go for the evidences. Look at the evidences. What are the things here available? You can see some bows are there, one axe is there, one gun is there, and a person is lying on the road, axe is on his back, and so are the bows. So do you agree that this is an accident? Probably not. So if it's not accident, then the null hypothesis, the probability of null hypothesis or probability that this is an accident, this probability should be very small, because it is quite impossible that by accident there are so many bows, they will enter someone's body. There is another one gun was lying there, and the axe was hitting just backside of that person. So combining all these evidences, we are quite sure that the probability of an accident is very small. So this is something what is called p-value, the concept of p-value. If your p-value is very small, that means there is high chance that the null hypothesis, what the hypothesis you are claiming, is not correct. So small p-value means that your null hypothesis is not correct. So this is one perfect example of rejection of null hypothesis. Here the null hypothesis was it was an accident, where we can see that this probability, if I assume that is an accident, then this if I multiply all these probabilities of all the events, that what is the probability that 4 bows will hit him, what is the probability that there will be gun just lying beside him. So the probability of every event will be very small, and if you multiply all these probabilities, it will be much smaller and resulting in a small p-value, and that means that your null hypothesis is not correct. So we can reject the null hypothesis. Okay, so this is the formal definition of p-value. So a p-value is a shaded area, is the probability of an observed result arising by chance. So what is the probability that the value we got it just because there is nothing except the chance factor is working. So you can see that as the observed data point goes towards right of the graph, your p-value will go very small and small. So that means most likely observation is at the middle, and if your data point is towards the right of the graph, that means your observed data point is far from the most likely observation. That means whatever we are saying is not correct, so now your null hypothesis will be rejected. So this is the definition of formal definition of p-value, that is the probability of an observed result arising by chance. So p-value obtained from an experiment represents the long-run frequency of obtaining data as extreme as the observed data, or most extreme, given that the null hypothesis is true. Okay, now we have this, all the time what we want, that my p-value should be less than 5%. 10 to the power minus 5 or minus 8, something like that, because they are doing multiple testing problem, and if they take 0.05, then probably all the genes will come into play. And Nature did in 2017, Nature did a survey, and there were that it should 0.05 to 0.005 they were wanting. So it's just an example to say that this choice of 0.05 is very arbitrary, and it shouldn't, and you cannot ask all the discipline to follow this norm that you well. So there are a few advantages of p-values also there. The first thing is that p-values are probabilities of certain events happening on the assumption that the null hypothesis is true. Conceptually, it's simpler than confidence-based methods because this depend on an argument involving various assumptions. This is flat pair assumption is something is Bayesian to derive confidence from probability. And if the null hypothesis is a credible or interesting hypothesis, then p-values do make some sense. However, for a non-technical or woefully misunderstood, to properly interpret p-values, one must understand their actual role in a valid testing procedure. And the p-value is not a valid decision rule, as it is not a type 1 error. So whenever we are using p-value, we must be a bit careful. P-value is a conveniently scaled test statistic. So that is very important. It is conveniently scaled test statistic. So after that criticism received from that journal, American Statistical Association, ASA, they issued a statement and they said you can't do some sort of things, and they issued a statement and they said you can't do some sort of things, and they put in a list. The first thing, don't base your conclusion solely on whether an association or effect was found to be statistically significant. So just p-value will not suffice. You cannot conclude just using a value p less than 0.05. Don't believe that an association or effect exists just because it was statistically significant. So suppose your p-value is 0.03, you are happy, and you are saying that association exists because they are statistically significant. You have to do some more calculations, or you have to give some more evidence to prove it. Only p-value won't suffice. Don't believe that an association or effect is absent just because it was not statistically significant. That is another thing. Suppose you got p-value of 0.07 and you were and move toward a greater acceptance of the uncertainty and embracing of variation. So you have to accept it, that variation will be there, and you have to deal with this, and you have to accept this uncertainty. Treat statistical results as being much more incomplete and uncertain than is currently the norm. So that is very interesting thing. It was mentioned in a paper in Trenfo and Greenland in 2019. They are saying that whenever we are getting any statistical result, you just see or consider this as incomplete and uncertain. What we do in real life, whenever we got this thing, is the value is what we are looking for. We are very happy and we are very confident. So they are saying no, you should consider this as incomplete and uncertain because you need to do more. About the world by forsaking the false promise of certainty, Thomas' declaration of truth or falsify binary statements about there being an effect or no effect based on some p-value or other statistical threshold being attained. So when Fisher introduced the concept of p-value, it was considered as a continuous measure. But nowadays, what we made it as a dichotomous. Whether p is less than 0.5, effect is present. If p is greater than 0.05, there is no effect. So it should not be like this. It should be a continuous thing. So you should be very careful about this dichotomous declaration, whether it's a truth or it's false. Now you may ask, if I accept the uncertainty, how will accepting uncertainty will change anything at all? To begin, it will prompt us to seek better measures, more sensitive designs, and larger samples, all of which increase the rigor of research. You all will agree with me that if you have smaller samples, it is very difficult to make any statement regarding the parameters or the scientific question you are asking. But if you can get more and more samples, then probably we can have better overview of the problem. So before collecting the sample, it is very important to make your designs, we call design of experiments, and this should be very sensitive. The problem, I work with a lot of scientists who are from biology background, and from that collaborative experience, I know that whenever I come up with some data, I found that there, in many cases, the design was very faulty. So if your design is faulty, it's just like garbage in, garbage out principle. If your data is garbage, then the inference will be also be garbage. Don't expect that statistics has a magic wand or it's a magic toolbox where you put anything and you get the desired result. It doesn't work in that way. So the design should be very sensitive. You should take better measures, and you take more and more samples. I know here a lot of questions will be there that sometimes the experiment is itself very costly, very time consuming. Then how can we get more and more samples? So yes, then that's true. But if it is possible, then try to take as many samples as possible. Accepting uncertainty as inevitable in a natural antidote to the seductive certainty falsely promised by statistical significance. That's why we are just recommending that you accept this uncertainty. With this new outlook, we will naturally seek out replications and the integration of evidence through meta-analysis, which usually requires point and interval estimates from contributing studies. This is the concept that people are accepting nowadays, meta-analysis. This is when, suppose you have done a study on a particular problem, and someone in UK or US or in some other part of the country, they are doing the same thing, and they have produced their results, they are published, their papers are there. You collect the evidence from those papers and do some sort of what we call is meta-analysis, so that you are getting, you can borrow much information from those published results. And meta-analysis nowadays is very growing. So this can help us whenever whenever we're saying that we don't have large samples, then probably meta-analysis will give you some avenue to work on. This will in turn gives us more precise overall estimates. Now the second part of the atom is thoughtful. In this perspective, we're talking about statistically thoughtful research. By statistical thoughtful, we mean that the researchers begin above all else with clearly expressed objectives. That sometimes it happens that whenever we are dealing with any problem, we just do just for the sake of doing it. So it should not be like this. You should put your thoughts carefully, and you should give it some time before making any sort of analysis. They recognize when they are doing exploratory studies and when they are doing more rigidly pre-planned studies. That is very important. We have a tendency whenever we have a data to run or to do some sort of tests, for example, t-test or ANOVA. But what I will say that whenever we are getting a data, first try to get some exploratory analysis. Just check how the distribution of that particular response is look like, whether it's bimodal, unimodal, symmetric, positively skewed, negatively skewed. So you need to do some sort of exploratory studies. And if you are thoughtful, then probably will do it. They invest in producing solid data. So that is very important. That sometimes what happens that we perform the experiment, but data collection or the storing of data is we make some serious mistakes, sometimes unknowingly, sometimes knowingly. So the data, the validity or reliability of the data should be there, and it should be something like that which can be reproduced if someone wants to do the experiment again and again. And secondly, it should be trustworthy. So because it may happen that on the basis of the data, if there is any chance of taking any policy decision, then if your data is not good, then probably that policy decision will not help us in. So they consider not one but the multitude of data analysis techniques. So you should view the problem from not only from the one angle but from the multiple angle. So it may happen that someone says that well, you can do some principal component analysis. You just think that is there any other method or other techniques available to do similar sort of thing. Whenever you try to see the data in a more holistic way, then probably you will get more avenue from that data, and your analysis will be more complete if you can think in that way, not in unidirectional way. Okay. So if in a big picture, if I say that what do we mean by thoughtfulness, there are three questions thoughtful researchers will ask. What are the practical implications of the estimate? How precise is the estimate? Is the model correctly specified? So these are the three questions I think all of us will face or already faced. That the first thing is that what are the practical implications of the estimate? We say that suppose the mean is 5.6, the standard deviation is 2.2. So what does this mean? What is the practical implication of 5.6 and 2.2? How precise is the estimate? That means we are questioning the reliability of the estimate. That if your estimate is very precise, so you are saying that, well, I don't know the exact estimate, it is something from -10 to 1200. No one is going to buy that. -10 to 1200, it's not precise. If say that, well, it's say 4 to 5, then or 4 to 10, even then that one is acceptable. So your estimate should be precise if it is not a point estimate. The third one, is the model correctly specified? Well, this question will again generate three more questions. The first thing, are the modeling assumptions understood? So you are saying that, well, I will do some sort of ANOVA with this data or a t statistic with this data. So what the assumption for a t test? What are the assumptions of an ANOVA? Are they satisfied? If not, then you shouldn't use that. So you will ask, are the modeling assumptions understood? Are these assumptions valid? So the basic premise of ANOVA is that your response should be normal, should follow a Gaussian or normal distribution. So what we'll do, you will just make a plot of this the response if it is the bimodal, unimodal, symmetric sort of thing, and you are happy with the normality assumption. So you have to make some sort of exploratory data analysis. Do the key results hold up when other modeling choices are made? So we are talking about the sensitivity of the model. So if you are thoughtful enough, then probably you will ask all these questions. What Anderson wrote in 2019, that modeling assumptions, including all the choices from model specification to sample selection and the handling of data, should be sufficiently documented so independent parties can critique and replicate the work. So that is very important, that it should be, or someone can replicate your work. Prioritize sound data production by putting energy into the careful planning, design, and execution of the study. That is what I was talking about, that your design should be very sensitive. You should collect your data in a proper way. You will take the measures in a proper manner, and you will produce a good solid data which can be replicated. So is this thoughtfulness through context and prior knowledge? This considers the scientific context and prior evidence, looks ahead to prospective outcomes in the context of theory and previous research. And what do we already know, and how certain are we in what we know? These are the few questions that a thoughtful researcher will ask. And building on that and on the field theory, what magnitudes of differences, odd ratios, or other effect sizes are practically important? So far what I was telling, that whenever I am saying it's important or significant, it's not just statistics. It should be in this scientifically. I should ask whether it's practically significant, practically important, and you have to consider all this thing in a carefully if you are thoughtful enough. The third part of this atom is open. Be open to open size practices. So it should not be like a closed one, that I got this and I won't listen to anybody. I got this p-value was 0.05 and everything is done, and I'm okay with this interpretation that this association is there, and I'm happy with that. No, it should not be like this. Your approach should be open, understanding and accepting the role of expert judgment, which enters the practice of statistical inference and decision making in numerous ways. So whenever you have some sort of these thoughts are available, you just incorporate those things. I'll give you one example of this. Suppose you want to know that how many tigers in Sundarban area, and what you did, you just make you say that what I will do, I'll just divide this area into different parts, and I'll visit that place, and I'll count number of tigers that I could see. Now suppose there you couldn't see, or you couldn't find any tiger during your visit. So from frequentist point of view, it should be 0. So do you agree that there is no tiger in the Sundarban area? Probably not. Suppose someone told you, the local person, that there were tiger yesterday, it was there. So this information, you should consider this information as very important information, and you can incorporate this in your model. That is what Bayesian people are doing. Whenever you have some sort of prior knowledge, they incorporate that prior knowledge mathematically, or I should say statistically, in the model building process, and they make this model more general so that it can incorporate different, it can incorporate or accept this sort of expert judgment. So this is one example where your approach should be open. Judgment is necessarily subjective, I do agree, but should be made as carefully, as objectively, and as scientifically as possible. So whenever I'm talking about this subjective things, that someone told me this thing, or in Bayesian terms where some priors are given, they might be some subjective, but it's not that subjective. It can be shown that even with that sort of information, you can get better inference. So this sort of subjective statement should be scientifically, should be as scientifically as possible. And this is the most important part, that openness is in communication, and that is where we are facing a problem. Be open in your reporting. Report p-values as continuous descriptive statistics. But what happens whenever we just submit a paper in a journal, we try to hide. We don't give everything that we got. So that's the problem in openness is communication. Use and interpretation of p-values will never adhere to a rigid rule book, and will instead inevitably vary from study to study. Failing to be open in reporting leads to what is known as publication bias. This is very important, that one study is rarely enough. So you cannot conclude anything from one study. And the words you will heard in news channel, a groundbreaking news study or something new has happened every day. This might be very loved by the news writers, but must be resisted by the researchers. They shouldn't flow in this with this sort of thing. That whenever we are claiming something, it has to be substantiated by the research, not only one study but by multiple study. In this regard, I can just point out the vaccine trial that has been going on in Oxford. So what they did, it is very scientific. The first phase, they started with healthy volunteers. So right now the results are quite good, but they have not introduced it in the market. Why? Because they know that the population they were working with, they have certain characteristics which may not be there whenever it's in the market. So they are healthy volunteers. Now what they will, and they within the age bracket 18 to 55. Now what they will do, they will remove these barriers and try to make it more general, and they will apply this vaccine to other peoples also. And even when they're happy with that, they find that the results, the outcomes, only then they will come into play. So it's not a one-day job. It's good for the news anchor saying that it's a groundbreaking work in a new study, and every day we'll find that there is a vaccine developed by Russia. Someday, then another news channel, they will claim that this is the first time we are saying that vaccine is invented in some XYZ country. So you shouldn't believe in these things, because the science requires some time to get a vaccine which we think it will work. It may happen that after doing all sort of things, it might not work. But anyways, that's how science progresses. So one study is rarely enough. This Oxford vaccine trial is one example where the one study has been completed, but they have not introduced the vaccine in the market amidst the pressure. They want more and more evidence. So being open goes hand in hand with being modest. So that is the final part, is called modest. Both scientists and the public confound statistics with reality. Statistical inference is a thought experiment describing the predictive performance of models about reality. Of necessity, these models are extremely simplified relative to the complexities of actual study conduct and of the reality being studied. So that is a limitation. Statistical results must eventually mislead us when they are used and communicated as if they present this complex reality rather than a model for fit. This is not a problem of our statistical methods. It's a problem of interpretation and communication of results. So whenever we are using any model, we are assuming certain things which may not be true for the real data. Even if just predicting the number of COVID cases, we fail. Sometimes we fail. Why it is so? Because we have not much info. We don't have much information about this virus because it's very new. So the models, whatever we're using, they will depend on some certain assumptions. If if it doesn't follow that way in how the disease progresses, then your model will not give you the exact results. So even if there are 1,000 models available in the market, hardly one or two they are close to the prediction. So they are close to the real data. The predictions are pretty close. But bearing this one or two models, the models are not working at all. So this is the problem, that in real life the situations are not that simple, and if complexity arises, then probably you need to think in some other ways. So behind every choice of null distribution and test statistics, there lurks a plausible family of alternative hypotheses which can provide more insight into the null distribution. That is very important. So even if your histogram is showing is a unimodal and symmetric distribution, but assuming normality, some may argue that why you are not using t-distribution or some other distribution which has similar sort of features. So unless you are very certain that it is Gaussian and all the inferences based on that assumption is not that firm, so you have to think about for the other plausible family of alternative hypothesis too. P-values, confidence intervals, and other statistical measures are all uncertain. So treating them otherwise is immodest overconfidence that we are suffering from this disease. That whenever we are getting something, we are happy with this. Don't consider this as certain. You just consider this as uncertain things, and you need to work more. The major focus of scientific inference can be viewed as the pursuit of significant sameness, meaning replicable and empirically generalizable results among phenomena. That is very important, that it should be generalized. I can generalize this thing at least empirically, and I can replicate the results. Regrettably, the obsession with users of statistical inference to report significant differences in data sets, so that's actively that will put some sort of hindrance in knowledge development. And we try to follow this one phenomena many studies instead of many phenomena one study. So if you do more study on particular phenomena, then probably you will get more information, and your inferences will be more accurate. Different readers may have their very different takes on the results of your analysis, which means you should try to take the role of a neutral judge rather than an advocate for any hypothesis. This is for the statistics people who will be doing some sort of collaborative research. You have to realize one thing, that you cannot dictate the other disciplines according to your terms and conditions. You must be neutral. You shouldn't have any bias regarding any sort of hypothesis, because you have to realize one thing, that the p-value for social scientists is not same as the biologist, because as I told you earlier, that for micro experiment, the p-value is something they consider to be less than 10.-8. So it's not the same. One model doesn't fit all. And this can be done, for example, by pairing every null p-value with a p-value testing an equally reasonable alternative, and by discussing the endpoints of every interval estimate. So once you get the p-value, your work doesn't end. I will say you start from that point and try to see in a more I should say holistic way that what sort of possibilities you have not considered, and you try to consider all those things and try to make your experiment or analysis more robust. Okay, so these are the final. I'll come with the final thing. I think I'm almost done with time. So these are the recommendations given by the American Statistical Association. The first thing is that replace any statement about statistical significance of a result with the p-value from the test, and present the p-value as an equality, not an inequality. So what does it mean actually? So for example, if you have p equals to 0.03, you should never write p less than 0.05. You just write p is equals to 0.03. Well, when suppose p-value is 0. There are 10 zeros, then there is 1 1. Then in that case, you can write p is less than 0.0000000, p is less than 0.0001 or 001. So that is meaningful. But in general, whenever you are getting p is 0.03, write it in the exact manner, not as an inequality. Likewise, if you have p is equals to 0.25, you shouldn't write p is greater than 0.05. So always express it 0.025. Okay. Present p-values for more than one possibility when testing a targeted parameter. For example, if you discuss p-value from a test of null hypothesis, also discuss alongside this null p-value with another p-value for a plausible alternate parameter possibility, ideally the one used to calculate the power in the study proposal. So you should consider more than one possibility. If you do an equivalence test, this is another example. Present the p-values for both the lower and upper bounds of the equivalence interval. So once you get the p-value, you just repeat this experiment once again. So what we are saying, that you just try to think about more than one possibility. Well, confidence interval is very important. Show confidence intervals for targeted study parameters, but also supplement them with p-values for testing relevant hypotheses. So for example, the p-value for both null and alternative hypothesis used for the study design on proposal, as in the previous point 2. And confidence interval is very important. They show that only what is in or out of the interval. And its more detail is often desirable for keep hypothesis under contention. So this confidence interval, if you give p-value along with the confidence interval that and sample size, then probably you are taking it in your paper in a different level. Now, when you are comparing groups, compare groups and studies directly by showing p-values and interval estimates for the differences, not by comparing p-values or interval estimates from the two groups of studies to 0.03 in males and p equals to 0.12 in females. It doesn't mean that the difference association were seen in males and females. Instead, what we want to do, one needs a p-value and confidence interval for the difference in the sex-specific associations to examine the between-sex difference. Similarly, if an early study reported a confidence interval which excluded the null, and then a subsequent study reported a confidence interval which included the null, that doesn't mean the studies gave conflicting results or that the second study failed to replicate the first study. Instead, one needs a p-value and confidence interval for the difference in the study specific associations to examine the between study difference. Okay, so in a nutshell, don't look for a magic alternative to null hypothesis testing. There we don't have any other alternative. It doesn't exist. Never draw a conclusion merely based on p-value. Even we seek for generalization from the data, we must seek to understand and improve them. And doing this, we need some detective work. We need to do more descriptive analysis, exploratory data analysis, report descriptive statistics and values of statistics apart from p-value, p-value, z-value, f-value, whatever you are getting. Report p-value with exact sign, not with less than or greater than. And this is very interesting. This is the main whenever we are taking any sort of decision on the basis of p-value. Suppose that we have two p-values, one is 0.04999 and we have another value 0.05001. So if I round off to 2 decimal digits, so both of them will reduce to 0.05. But what you did actually, 0.0499, you are happy. And whenever it just crossed the threshold 0.05, then it's you're gloomy. Why is it so? Because these two values are more or less like the same, but your inference are quite different. So treat p, which is close to 0.05, as an interesting but unconvincing support for an isolated null hypothesis test result. So p equals to 0.05 warrants publication without replication. You have to look very closely. So whenever your p-value is close to 0.05, you don't feel very comfortable that it's 0.044, and I'm very happy nowadays. The editors of any good journal, they may ask that your p-value is close to 0.05. You should look at the data once again and just double check whether it can be 0.05 or it can cross 0.05. So something this is very interesting, that even if we have some sort of biasness about this 5% level, these two values 0.0499 and 0.05001 are the similar things, but your inferences are quite different. Report results for all important hypothesis tests. So this is openness is there's a problem we face in openness of communication. The selective reporting is a well recognized flaw of null hypothesis testing. We don't report everything. We report the p-value which is less than 0.05. There exist several methods for an upward adjustment of p-value. Suppose you have done multiple tests and you have to give all the results. It's not that like the end product you are giving. You have to say that I have done 5 tests and for these p-values are there, and combining these 5 tests, I am making an adjustment of the p-values, and the p-value is reported as this. So for example, consider a researcher who has used null hypothesis testing in a series of 5 tests of the same hypothesis, only one of which yielded a null hypothesis rejection. So what he or she did, he or she reported only that hypothesis which yielded a null hypothesis rejection. It should not be like that. You should have considered all 4 cases and you made some sort of correction using something like Bonferroni's correction, and you just say that your combined p-value is this. So this sort of thing is that whenever you shouldn't do any sort of selective reporting. Whatever results you are getting, you should mention each and everything. Report enough data to permit secondary analysis. Routinely report effect size in the form of confidence limit, which contains all information to be found in significance test and much more. And we don't sometimes we don't report them intentionally. Suppose your confidence interval is very large, something say 10 to 12,000. Suppose you have done some odds ratio, and you found that the confidence interval say 10 to or 0.5 to 200. Now you know very well that 0.5 to 200 is not very good thing to show, so you just suppress that thing. Larger sample sizes reduces the size of the confidence interval as they increase the statistical power of null hypothesis testing. So we need more and more sample to have precise confidence intervals. And whenever you have done your analysis, it is done, you should put much emphasis on clinical or practical significance instead of statistical significance, because ultimately that is going to work, not your p-value. So this what is the clinical or practical significance, whether there is any significance or not, that is very crucial. I think I'm done with my presentation. So this is my favorite quote: a statistician is a person whose lifetime ambition is to be wrong 5% of the time. Stay safe. Thank you.
Thank you, Dr. Chakraborty.
Oh, just
I now request Narayan Prasad to unmute your microphone and
Yes, sir.
ask about your query.
Yes, sir. Before going to test the p-value, we have to see whether our data is normal or not. So there is a problem. Actually, I'm dealing with the empirical study. So I'm not getting the normality in data. So what are the ways so that data can be normal?
Okay, you can view in this that you can make some transformations like log transform. And if you still find that the data is not unimodal, or then there are ways to deal with it. You can go for non-parametric assumption. So for the t-test, we have alternative in t, ANOVA, everything. For a t and ANOVA, we have all the tests available in non-parametric setup too. So you can think of that way also. Then instead of going for the parametric testing, you can go for the non-parametric tests. The softwares are these options are available in each and every software.
Okay, sir. Now the thing is that, sir, actually I am collecting the data from the primary sources, and I'm using the Likert scale. So suppose 1 to 5 scale, and maximum are responded giving 4 or 5 or 4 or 5. So in this case, I am getting 4 and 5 many value. So it in a graph, it is giving a tail. So how to reduce this tail? This is the main problem I'm facing right now.
Well, for your data, it's a specialized data. This is categorical, it's ordinal data. And whenever we have ordinal data, it's not possible to use the simple techniques we know. You have to use some sort of cumulative logic model, or you have to using some latent variable model. So models are there, but they are a bit tricky. And as you mentioned, one interesting thing that most of them are saying 4 and 5. Then probably you won't get much information from that data, because there will be heap of data in 4 and 5, and there won't be any data from 0 to 3. Then those things are becoming redundant. So this is a very specific problem, and this specific problem needs a specific solution too. So I don't know that what you will do, but apparently it seems that seems to me that it's you need to use some techniques which are available or which are used for the ordinal data. You just look for the internet and you look in Google, and you will definitely find all these theories.
Okay, sir.
Thank you, Dr. Chakraborty. Thank you once again. I now request IQAC coordinator, Dr. Omoris Mondal, to give the vote of thanks. sir, please.
Hello. Hello. Am I audible? Hello. Hello.
Yes, sir.
Am I
Yes, sir.
audible?
Yes, sir. Yes, sir. You are audible.
Yes.
Thank you, Subroto. Thank you, Subroto. Good afternoon, everybody. This is the time when short talks, toast, and gracious words are in demand. Be inspired by these words on thanks, joy, and gratefulness. According to Gilbert K. Chesterton, I would maintain that thanks are the highest form of thought and that gratitude is happiness doubled by wonder. Honorable Chairperson, distinguished speakers, their support staff, my esteemed colleagues of the Department of Statistics and other departments of the college, beloved students, and respected other participants of the webinar. It's my privilege to have been asked to propose a vote of thanks on this international webinar on application of statistics in contemporary issues, organized by the Department of Statistics in collaboration with Internal Quality Assurance Cell of the college. I, on behalf of the IQAC, Krishnanagar Government College, and the Department of Statistics, extend a very hearty vote of thanks to our most valued speakers who blessed us with their presence and took out the time of your busy schedule. I must mention our deep sense of appreciation for Srimati Madhav, who secured MBA from University of Cambridge, MSc from IIT Bombay. The City Group Treasury, City Global Markets, London, United Kingdom. For her wonderful presentation, I would like to express our sincere thanks and appreciation to Dr. Arindam Chakraborty, Assistant Professor of Statistics, Vishwabharati University, for his excellent presentation on his from confusion to conclusion value. I would like to emphasize that they attend all the participants of the webinar. I express my gratitude to our in charge, Dr. Nyogi, for showing encouragement and support organizing webinars. To Dr. Subroto Rana, Head of the Department of Statistics, and his departmental faculty, Sri Gautam Burman, for their successful organization of this webinar. Dr. Indrita Saha, Assistant Professor of Geography and member of Internal Quality Assurance Cell, has extended her wholehearted cooperation to maintain uninterrupted technical support during the webinar. I express my hearty thanks to her. Once again, I would convey my thanks to all members of Internal Quality Assurance Cell, all my colleagues, students, and all participants for their active participation in this webinar. Thank you everybody for making this webinar successful with your contribution. Thank you again. Thank you all.
Thank you, sir. As it is described in the brochure that This is a webinar series or international webinar series on application of statistics in contemporary issues. And this was the first chapter. So the Department of Statistics of Krishnagar Government College will be presenting or will be organizing its second chapter in couple of weeks. And for the present session, it is now concluded that the session is completed. Okay, thank you everyone.
Hello. Hello.